Okay. Now we are proceeding towards understanding what is the total stress tensor. Why did we call as total stress tensor? What are the components? What is the meaning for the word total there? Okay. Now to do that, we will have to understand distinction between solids and fluids. Okay. That is what we are going to do now. Okay. Very nice table from this book by Shogunese and others, Introduction to Fluid Mechanics. What this table shows are the characteristics on the first column, and then these characteristics are listed for solids, and then fluids. Within fluids we have liquids and then gases. Now there are several characteristics listed, several properties listed. We will discuss these properties in two sets. First the highlighted properties we will discuss, then the unhighlighted properties will be discussed, okay, which of course I will highlight later. We will understand what is the distinction between these two set of properties. The highlighted properties here are very well known to us, every one of us will easily know these differences. The other difference are something very special to this mechanics of fluid versus solids, so we will discuss next. Okay, what we are going to discuss is just a revision of what you already know in terms of differences between solids, liquids and gases. So let us go through that. Distance between adjacent molecules, smallest in solids, small in liquids, large in gases, known to us. Molecular arrangement, ordered, in gases it is random, so liquids we can say semi ordered. Okay. Strength of molecular interaction, of course strong in solids, intermediate in liquids and weak in gases. Ability to conform to the shape of a container. If you take a container and put a solid, that will have its own shape, so it will not conform to the shape of a container. If you take a liquid, yes, it will take the shape of the container itself. Gas certainly yes. Okay. Capacity to expand without limit. Okay. Now if you once again take a cylinder, that is a good example to take, and then take a cylinder, let us say the piston, and then you take a solid, that will occupy its own space. Okay. So it cannot expand, and if you take a liquid, once again it cannot expand to the entire region. It will, whatever volume it occupies, it will occupy only so much volume. But suppose if you fill the gas and you keep expanding the cylinder piston larger and larger away from the bottom surface, the entire space will be occupied by gas. So that is why it says capacity to expand without limit is S for gases. Ability to exhibit a free surface, if you have a solid, it exhibits a free surface. If you take a liquid inside this, it exhibits a free surface, but gas you cannot define a free surface. Okay, no. Okay, so these are the differences well known to us. We have just revised it, I would say. Okay. Okay, so now we are going to discuss the difference between solids and fluids, which will lead to our understanding of the total stress tensor. What I have shown on the left hand side, we have taken two plates, okay, and then let us say we have a solid object, that is too heavy. Okay. Let us say we have a solid object, imagine it is completely solid, and I have a solid object between these two plates, and this object is fixed to the bottom plate, and then I am applying a tangential force to the object is fixed to both the plates, I am applying a tangential force to the top plate, and that is what is shown here. Stationary rigid bottom plate and a rigid upper plate in contact with the sample, and then you are applying a tangential force. Now what happens, of course I can show that here, the solid object deforms for our case we can take it as, we will see what formally deformation is later. Right now we will say change in angle, okay, slight change in angle, that is what you see here. Let us say in front view it was a square, it became something like a parallelogram, okay. That is what is shown here in 3D, and that is shown here in the front view. If you mark points D and C to begin with, they would have moved to D dash and C dash. So now what happens, it starts deforming and internal shear stresses develop because of the external tangential force. Now what happens, this deforms until the internal shear stresses balance the external force, and most important word is it stops deforming, that is all. It was one state, it deformed, changed in angle. So it from one equilibrium state it went to another equilibrium state. So it means it has resisted the shear stresses under static condition. These are very key words, of course I will summarize in the next slide. What happened, there was a change in angle, and then you remember you continue to apply your tangential force, you have not removed it, continue to apply the tangential force. There is a deformation, in our case change in angle, that happened and until the internal shear stresses balance the external force, and then it stops deforming. After that it does not move, okay, something like it is resisting the shear stresses and it is static also, okay. And after that it is independent of time, okay. This may happen whatever time period, but after that is independent of time. That is why we say it goes from one equilibrium state to another equilibrium state. Now if you remove the force, what happens, it will go back to the original state, okay. Of course all these happen at the micrometer level, we can't so easily see. Even when you apply a megapascal, let us say force per area of that order, then these changes will be something order of 10 power minus 6, that is the scale. So in that way it is little certainly difficult to see by naked eye, but you should be able to imagine yourself. So that is what happens for solids. One more explanation can be given by using the cylinder. I will give the same analogy in terms of this Cartesian coordinate, that is in terms of cylindrical coordinates. Now there was some equilibrium state. Now the force required for this deformation depends on how far it is from the original equilibrium state. If you want to deform further and further, let us say you have d dash here, you have c dash here, so more force is required to deform further and further from away from the original equilibrium state. So it depends on the angle for our purpose. What happens here in the cylinder, let us say in the cylinder you put a solid and you want to, let us say you are interested in the force required to rotate the inside cylinder, okay. Now the force required depends on how much you want to deform the solid from an initial state or initial equilibrium state, how far you are away from that, okay. All these keywords will keep understand when it is distinguish fluids, okay. So how far from the original state matters in the case of solids, okay. So that is what happens for the case of solids. Now let us take the case of fluid, okay. I think the configuration is something known to us for the case of fluids. We have come across a few times in our earlier lectures. We said we consider flow between two parallel plates. So we have come across configuration few times, and many times what I have come across is where both the plates are fixed. Few times I come across a configuration where the bottom plate is fixed, the top plate is moving. That is a configuration we are seeing here. What is shown here, a bottom plate and then a top plate which is moving. So now instead of this imagine this to be a fluid body instead of a solid body, and then it is between two plates, and then you are applying the tangential force. There also you continue to apply the tangential force, here also you continue to apply the tangential force. Now what happens in the case of fluids? If you see here, this shows the configuration of the fluid, or let us say shape of the fluid object, and then it has undergone some change. After some time if you continue to apply, it has the angle has further increased, and that is what is shown here schematically. Let us say to begin with you mark points D and C, after some time it moves to D dash C dash, moves to D double dash C dash. As long as you continue to apply the force, tangential force, it continues to deform. Look at the distinction between solids and fluids. What did we say? For the case of solids, it deforms and stops deforming, no further deformation. That is why D became D dash C dash, that is all. That is why you said it went from one equilibrium state to another equilibrium state, but now there is no such static condition at all, it continues to deform. So what does it mean? if it is stationary, it cannot resist any shear stress. Moment you apply even a slightest shear stress you apply, slightest tangential force you apply, it will start moving. So, that is why we say that fluids cannot resist shear stress under static condition. Moment you apply, it starts moving, and as long as you continue to apply, the fluid deforms continuously, and that is why we say fluid flows. I did not use the word flow for solid. For the case of fluid, because it continuously deforms, as long as you apply, we say the fluid flows. Okay. Now, what happens if you remove the tangential force? Just retains, there is no regaining the original shape, there is no preferred shape or anything for fluids. So, if you leave at this, leave meaning you stop applying the tangential force, that is all, it will just stay there. So, it just retains the final state. Okay. So, now in terms of other way of explaining is that there is no change of angle I can talk about from some initial state, always that change of angle is 0, because every instant there is a shape and the deviation from that state is 0. So, I cannot talk about a change of angle, I will understand shortly. Now, as we explained for the solids, let us take in this case, I interested in the force required to move this plate. Now, this will not depend on the angle, but it will depend on the rate at which the angle changes. It will not there is no preferred or something called initial state. So, I cannot talk about a change in angle from initial state, but if you want to move the, let us say move the fluid faster, then you require larger force. So, it depends on rate at which deformation takes place or rate at which the angle changes. Easier to understand in terms of this cylindrical geometry. In between the two cylinders, you now have a fluid. Now, let us say as earlier you are interested in the force required to rotate the inside cylinder. Now, it depends on how fast you rotate the inside cylinder. There is nothing like a state how far. Earlier we said the force required depends on how far we are from the initial state. For the case of fluids, it depends on how fast we rotate the cylinder, it depends only on the rate of angle change or rate of deformation. These two differences, deformation, rate of deformation, etc., we will discuss again later in detail. Okay. I will also demonstrate this. I think this slide we have discussed earlier when we discussed a demonstration of a system. So, this slide is same as what we discussed earlier. We have come across this slide when we wanted to demonstrate a system. In fact, the same slide is there, I just changed the title to fluids deform continuously. So, same demonstration can be shown now to show that fluids deform continuously. Okay. The configuration is well known to us. Now, earlier we said I dye a particular region of fluid, and then what happens when the focus on that particular region, etc. Instead of that, just slightly change our imagination, change our visualization. Instead of saying you identify a part of the fluid and call it a system, just like in our previous slide, the next slide you imagine in line with this diagram or in line with this whatever I am showing you. Okay. So, what we have here is, imagine we have two plates and the red now represents the whatever region of fluid which are discussed. Now, when you start applying the force, let us see what happens. We have seen this video earlier, but the interpretation now, earlier we viewed this as a system and you are following the system. Now, you view this as a volume of fluid and then that deforms continuously as long as you apply the force. Of course, this video is limited, it may come back, but otherwise in general, see, as long as you let me stop here, as long as I continue to move the top plate, this fluid continuously deforms. Okay. That is why we say the fluid flows. Okay. Okay. So, now we have seen in different ways the difference between solids and fluids, etc. Let us summarize them. Before that, let us look at the differences which are not discussed. Same table, the differences now will become clear after our distinction between solids and fluids. Okay, what are the differences? Look at the first difference. The first difference is response to shear stress. Okay. We have discussed now how does a solid respond to shear stress, how does a fluid respond to shear stress. Now resist deformation, this resists rate of deformation. There is no discussion of angle, but here it is rate of change of angle. Okay. That is why we said here, we said how far from the initial equilibrium state, but here the force depends on the rate of change of angle, the rate. Okay. Once again, this particular difference we will discuss again and then discuss later as well. Okay. Now what are the other differences? Able to resist a small tensile stress. What does it mean? Let us say you take a floor and then you add water and then you apply, let us say, this plate. Okay. Now of course you are applying a normal stress, but if you look at this direction, it is tensile, you are applying a normal stress perpendicular, but if apply look at this direction, it looks as if you are applying a tensile stress to the liquid. Okay. Take a, let us say, a small pool of water and applying, let us say you apply this force on the plate. Now the liquid spreads, becomes thinner and thinner and thinner. Okay. It is equivalent to applying a tensile force in this direction. Okay. Now let us discuss. Okay. Ability to resist a small tensile stress. What does it mean? If you have a solid object and if you are applying a tensile stress, tensile forces opposite each other. Okay. You have a solid and then of course I will leave it in air. If you apply a tensile stress this way, then it will resist the tensile stress. Yes. Okay. In terms of liquids, you can theoretically say yes, but practically, as I explained you, as long as you apply this normal force, it keeps on thinning and thinning, which means that it just extends. Practically there is no ability to resist a tensile stress, becomes thinner and thinner and thinner, which means that it keeps on expanding. So practically no, theoretically yes. Always this, if you look at the differences, the properties of liquids are in between, of course, solids and gases. That is why you look at words like semi ordered, intermediate, etc. Here also it is intermediate behavior. Of course gases certainly cannot resist tensile force. What does it mean? Same, let us say you have a gas in a cylinder and let us say you have some two pistons like this, you expand, as long as you expand it will just keep expanding. So there is no resistance to tensile stress. The last line difference, of course, well kind of known to us, but relevant to this particular discussion. Compressibility essentially 0, that is why we can't even see the change. Gases highly compressible. Once you discuss these two, easy to mention about liquids, virtually incompressible. Always there is a kind of ambiguity when you discuss liquids. They are almost like gases, but not like gases. Okay. That is why virtually incompressible. Okay. Use words like theoretically, practically, virtually incompressible. For gases it becomes clear highly compressible. Okay. So now let us distinguish solids and fluids. This is just summary of what mentioned. Okay. Solids resist shear stress under static condition, that is important. Okay. Fluids cannot resist shear stress under static condition even for very small shear, which means that if a fluid is stationary, there is no shear stress in a stationary fluid. If you apply a shear stress, immediately it will start moving. That is the way you should look at it. Two different, same concept, two different ways. Remember, why the reason for highlighting this is that this is the point we are going to take forward. Okay. So that is why highlighted. We will repeat again. Solids resist shear stress under static condition. Okay, under static condition. Fluids cannot resist shear stress under static condition, even for infinitesimally small, very small shear stress, they just start moving. We will take this point forward in the next slide. Now solids reach an equilibrium stage, we have discussed it goes from one equilibrium stage to another equilibrium stage and then stops deforming, that is all, they just stop deforming, no more further deformation. We have seen for fluids, both in terms of explanation, in terms of video also, deform continuously, that is why we say fluid flows. And in the case of solids, we said if you remove the external tangential force, it regains the original shape. Case of fluids does not return to the prior shape, just retains the current shape whatever configuration. Okay. Force depends on deformation, in our case change of angle, force depends on rate of deformation, meaning rate of change of angle. Okay. So, these three the last 3 points, okay, I will repeat this again and that is what we will discuss later on. Okay. Right now the most important distinction for our present discussion is that a stationary fluid there are no shear stresses. If we apply the most smallest shear stress, it will start moving.